Good afternoon everyone, and welcome to Codebase Alpha. This is episode 57 and it's a pop-up stream because I didn't manage to stream successfully on Wednesday because of a bad headache, and then the rest of the week kind of just ran away with me and I couldn't actually manage to do a scheduled stream. So this is in place of Wednesday's stream, and it's a continuation of the work we started on the Synthesizer project. So if you were with us last time, we started work on a project called NanoSynth, which is basically going to be a test bed for our synthesizer objects that we're going to create in C++, and we're using a system called RackAFX version 6. And I explained kind of all the background to that in the last stream. But if anyone has any questions on that, just feel free to ask in chat. So let's have some background music going, shall we? Hopefully that's not too loud. And let's pop over into the code and see where we are. Okay, so this here is RackAFX, and what we can see here is the kind of rapid prototyping system which RackAFX provides us with. So rather than when we were kind of working with Juice and C++, having to faff around creating all the Gui controls to test out our plugins, this comes with a rapid prototyping system. So it's got a whole bunch of sliders, a whole bunch of radio buttons. It's got a fancy LCD control up here. It's also got output gauges. It's got a scope, and it's got input and output dB VU meters down the bottom here as well. So it's quite good from that point of view. So let's get started. So today we're going to start to build the oscillators. So our kind of first synthesizer we're going to build, which is the NanoSynth, is going to have two pitched oscillators, and they're going to be analog modeling oscillators, and we're going to have a low frequency oscillator, and we're going to start off by building the low frequency oscillator. And the low frequency oscillator, as the name suggests, is below audible range, so it's in the range of 0 to 20 Hertz, so below the range of human hearing. But its job is not to make a sound, it's actually to modulate other controls, so to vary other controls, so to provide effects like vibrato or stuff like that. We can start off actually by creating some GUI controls. We've got a couple of controls we're going to need to do. We're going to need to be able to select the waveform for our pitched oscillators and for our LFO. We're going to be able to choose the mode of our LFO, and also the depth or the amplitude and the frequency of the LFO. The frequency of our pitched oscillators will of course be controlled by our MIDI keyboard. So whichever note you press, that will determine the frequency of the audible sound. So let's start. So what we can do is right click on this slider, for example, and this can be, we'll give it a name. This is going to be, we'll call it our oscillator waveform, like that. And it's going to be an enum type of slider. So at the moment we're in the prototyping system. We're quite limited in terms of these sliders look like sliders. So this is going to be a step slider, go through an enum. But in the full GUI designer, which we'll use once we've got everything working, we can actually choose different styles like knobs or whatever really. So there's different styles we can do. We'll come across that later. We're not quite ready for that yet. So we now need to give. So this is going to be an enumerated type. So let's put the enumerated types of our that our oscillator can provide. So there's going to be sine. I'm going to put these in capitals. So there's going to be the sine wave we can produce, and then there's going to be three different types of saw wave. So we'll have those. Saw 1, 2 and 3. There's going to be a square wave. There's going to be a triangle wave. Let's put triangle before square. And there's going to be a square wave. There's going to be a noise. And we're also going to have pink noise. So we call that P noise. There's the different types of waveforms our oscillator is going to create. And we need to give this a name now. So we'll call this, now we're going to use Hungarian notation. It's not something I'm particularly fond of using, but on the principle that the files that RackAFX generates are all in this Hungarian notation, and we should follow kind of team conventions, then that we're going to actually stick with it. So this is going to be an unsigned int under the covers, and we're going to call it, what should we call it? Os waveform, I guess. And that should be sufficient. So let's click on that. And we should have now our oscillator waveform here. And it's, see, you can step into the different values. It's not a continuous control anymore. So hopefully that will be fine. Let's just double click on it, right click on it again, and make sure everything's okay. So yes, we've got this, the 1, 2, 3, 4, 5, 6, 7, 8 options, 0 to 7. So that looks fine. Okay. So the next thing we're going to need to do is have a similar kind of control, which is going to select our low frequency oscillator type. Hi Silly Dev, welcome. Who's Charles Simony? Not sure of the reference. Welcome to the stream, good to see you. Okay, so this is going to be another enum. And we're going to call this M_U LFO, and I'm going to put a 1 after it because some future designs of synthesizer projects may well have more than one LFO. I'm very well, thank you, Silly Dev. How are you? We're going to call this waveform LFO1 waveform, like that. And we're going to give this. Now you can see we actually stored the last enum down here, so we could reuse it, but we're going to keep it separate. So this is going to be our different types of waves that our LFO can create. So this, remember, this is a modulating oscillator. It's not a sounding oscillator or pitched oscillator. So we're going to produce a sine wave. We're going to produce a unipolar saw wave. That is a saw wave which goes from 0 to 1. We're going to have a bipolar saw wave, which we'll call D saw, which goes from -1 to +1. We're going to have a square wave, and we're going to have something called RSH and QRSH. So these are they're like a random noise, except they produce a random sample and hold it for a definite period of time. So they're kind of random shot and hold. So that's kind of what the idea of RSH is. And the QRSH is basically an inverted version of that, so multiplied by -1. Okay, so that is that. So we need to give it a control name. We're going to call it LFO waveform. We can call it LFO1 waveform if we want. So it's okay. Let's see if we can save that. So now that's in this one, LFO waveform. And now we need a mode for our low frequency oscillator. This is going to be another enum. We'll call this LFO1. Get rid of the extra 0. U LFO1, forgetting the Hungarian notation already, and this is going to be mode, and this is going to be sync for a synchronized Oh, so Hungarian notation. Okay, so he's the inventor of that, is he? I see. Okay, so I'm not really fond of it, but we're going to fall into the usage of it for this project. So sync, the mode of sync for your low frequency oscillator is when the oscillator starts when a MIDI note comes on and stops when the MIDI note is released. So a note on or note off event will switch on the oscillator and switch it off, the low frequency oscillator is. The other mode we're going to have is called a shot. A shot mode. So what happens here is that when you press a note on, it will go through a single cycle of the low frequency oscillator and then stop. And then the final mode is going to be free running, which we'll just call free, which means that when we press a note on, the oscillator is going to start running, and it's going to continue. If there's notes on or off in the background, it's going to continue going on. So as you're playing the keyboard, the low frequency modulator will be at any kind of random position in its cycle, depending upon how much time has elapsed since the first note was played. So that's going to be that. So that's our where did that appear? Didn't we give it a control? No, we didn't. So this is going to be LFO1 mode. There we go. So that's appeared here, and then we're going to have the rate. So this is going to be a continuous slider this time. It's going to be, we're going to have it as a double. It's going to go from, this might seem strange, but it's going to go from minus 0.02 all the way up to 20 hertz, 20.0 hertz. The initial value is going to be, let's say, I don't know, 0.5, half a hertz. Units is going to be hertz. The variable name is going to be m_d, and then what should we call it? LFO1 rate. That seems okay. Let's make a capital R. LFO1 rate, and this is LFO1 rate. That's basically the frequency. It's going to be linear control, parameter smoothing. We could put parameter smoothing on if we wanted to. I don't think it matters particularly for a low frequency oscillator. So let's hit that, and we should have LFO rate here, and then finally down here we'll have the LFO depth, or the amplitude basically. So this is going to be LFO1 depth. It's going to be a double again, not a number, double. We're going to call it m_d LFO1 amplitude, because that's what it is, the rate. This is going to go between 0.0 and 1.0 with an initial value of 0. That's fine. So that should be okay. Okay, so we got our LFO depth, and what's that been doing in the background? It's been basically updating some of our code. So if we go over to nanosynth.h, we should see some changes in here. So let's just have a look at the compare with unmodified, and we can see that what we've got is the values that I've just the variables I've just created have now been created here. So they're added by RackAFX, and it says do not edit this code. So here we have the enums that I created for those controls, and also the uints, and then the two doubles. Okay, so those have been created for us in our header file. We haven't got to worry about creating them ourselves, which is a kind of a big bonus for us, really. In that, you know, the problem with Juice, it seemed there's a lot of kind of manual stuff I had to do, which was a bit boring, really. So that's that. Okay, so we're now going to look at these files. So these are the oscillator.h and the oscillator.cpp files that come with our project. And these are the base classes, basically. Define a base class called OC oscillator. So C oscillator, sorry. and you can see here's the class definition with it, and it's got some virtual, pure virtual methods which we're going to have to override. So these two, start and stop oscillator, and there's a do oscillate, there's a set, there's a reset, and I think that's it, and obviously the constructor and destructor, which are up here. Okay, the rest of it is pretty much we're going to be able to use as is. And now the way our oscillators are going to generate their hi Copper Birdie, welcome to the stream, good to see you. The way they're going to generate their samples to create the waveforms is what's called a modulo counter. And the modulo counter is very simple. It's a counter which starts at 0. It increments by a variable increment value. So the increment is set by, basically you work it out, it's the frequency of your oscillator divided by the sample rate. That's how much it's going to increase each time. And when it gets to 1, or when it exceeds 1, it resets to basically the value it got to minus 1. So it's going to step up between 0 and 1 and then wrap round. That's called a modulo counter, and that's what this MD modulo thing is. It's a modulo counter. So you can see here it is incrementing by the value of the inc, and the increment value is defined. Well, you can find where that's defined. It's defined as, so the frequency of your oscillator divided by the sample rate. That's your increment, called the phase increment, the phase, whatever. And then you've also got these checks here. So what it's doing here is saying if you've exceeded 1, then wrap it round. In other words, take 1 off the value, and that's your new value of your counter. The same if you've got this idea of negative frequencies, which is a bit of a weird idea, which we can explore at some point. Then it does the same, it adds 1 to it. So it's basically keeping your modulo counter in the range 0 to 1.0. And that's how we're going to generate all our waveforms. I'm not going to go too much into the algorithms. The algorithms are all embodied within this header file called synth functions. Oops, let's get rid of that. But we may look at some of the algorithms at some point. But I'm not going to bog us down in mathematics, because some of it can get very mathematical. For example, we're not going to use the sine function. At least not very often will we use sine function. We're going to use an approximated sine, which is called a parabolic approximation, and it's not too difficult in terms of the formula. You just copy the formula off the internet and kind of implement it in C++, but it's a bit kind of much to try and understand exactly how it was derived. Okay, so let's create ourselves a header file. Let's add a new item here. It's going to be a header file, and we're going to call it lfo.h. Okay, so what we're going to do here, we're going to define the class LFO. So using the syntax of C++, we get class, we're going to call it CLFO, so class LFO. Once again, we're adopting this Hungarian style notation for this, and we're going to inherit from the oscillator base class, like that. If we spell it right, it would really help. We're probably going to have to hash include let's see, it's called oscillator H, like that. I think it is an os. That is correct, the name, I believe. Let's just grab the name out of here, just in case I spelt it wrong. Oh, it has. It's picked it up now. There we go. Okay, good. So we're going to have some public properties on this, and they're going to be our CLFO constructor. That's going to not have any values passed through to it, and then we're going to have a destructor, which is the squiggle, CLFO, like that. And then we got some overrides we need to do. So the things we need to override are these pure virtual methods down here. Okay, so we've got pure abstract things: start oscillator, stop oscillator, do oscillates, reset. I think that's it. Just those four. So virtual, void, reset, virtual void, start oscillator, virtual void stop oscillator, and there was do oscillator, I think was the last one. Do oscillate. Spell virtual correctly. There we go. So that should be our header file. Okay, so now we need to create a Cpp file for this. So let's add those down here. The new item is going to be a C++ file. It's going to be called LFO. I'm going to add that. Okay, so we're going to need to hash include LFO.h, and that will in itself include the let's also put that pragma in there. Pragma once. Make sure we only load files up, include files up once. Okay, so we need to build a constructor. So the LFO. So that CLFO is the namespace, and it's a void constructor. There's no values being passed in, and in here we're going to set the mode, the initial mode of our low frequency oscillator. So if I go over to the oscillator.h, we should find in here the name of the mode, and it is it's in here somewhere. It's there. It is MULFO mode, to store the mode. So let's grab that variable and pop it over into here, and that's going to be equal to we're going to put it in synchronous mode to begin with. Sync. Okay, so that's that. We don't need a destructor, I don't think. But what we can create now is start to fill out some of the values of some of the definitions of the functions we've overwritten. So we had a reset like that. Let's get the oops. Let's get them written out first. Then we've got start oscillator, haven't we? So that's a void as well, as far as I remember. CLFO : start oscillator. and we want void CLFO stop oscillator, and the last one was void CLFO namespace is that, and this is going to be do oscillate. Looks like we've got a spelling mistake over in here. We have, yeah, there we go. So do oscillate is now correct, and that's going to be do oscillate like that. Okay, right. Let's have a look. So let's start to fill some of this stuff out. So we can call on when we do this this reset. We can just call the base class at this stage. There's nothing special we need to do. C oscillator reset. So here we can obviously we can override that function. We can put some special code in there if we need to. So start oscillator. So if we're not in free running mode, we need to do reset, i.e. start the waveform from its starting position. If we're in free running mode, we don't need to do that, because it's going to we just accept whatever it is at the point where we press our note. And we also need to set there's a flag over in the oscillator which is called note on, which it should be over here somewhere. Yeah, note on. So that means we've actually got a note that's being played by the musician. He's got there's a MIDI note event happened. So we need to record that. Okay, so basically we can reset if we are we can reset the oscillator if we're not in free running mode, can't we? So we can say if MU LFO mode, which is what we recorded, equals sync, or LFO mode is shot. Then we can call oscillator reset. We can call reset, in fact, our own reset, just in case we do put some values in there. And that's that. And then we can set our flag, our Boolean flag note on to true, just to indicate to the oscillator that we've got actually a note being played. So stop oscillate. Basically, we just need to clear that flag, don't we? If we set it on start oscillate to that, on stop oscillate, we need to say there's no longer a note being played. Okay, so that's that. Right. So what does do oscillate look like? Let's have a look at do oscillate. The do oscillate looks like that. Okay. So this is so we've got an auxiliary input here, which defaults to null, so we don't have to pass a value in. And it looks like is used for what's called quad phase output, which is the inverted output of the low frequency oscillator, or for a pitched oscillator, it's actually the right channel in a stereo setup. Okay, that's interesting. So what we want is something along the same lines. Okay, well, let's try it over here. We don't want to, because this is the LFO, and we know for an LFO this is quad phase output. Oops, didn't want to do that. Let's Control C that. We can call it quad phase output. So it's a pointer. So we'll call it P quad phase output. I was thinking, are we doing the right thing here? What's do oscillate look like over here? We haven't got a do oscillate defined. Oscillate here. So it's a double, virtual double, and it has that. So I think our definition over here, this needs to be a double. And it also needs to have the same kind of setup as this. And that needs to be a double. Okay, looks a lot better. Okay, well, so if the rotes, so we need, if there's no note on, we don't want to return any samples. Is the first thing we need to note from this. So what we can say here is if that Boolean flag we set earlier, note on, if it's not true, it's not on, then we can say so we need to take care of that quad phase output. So if P quad phase output, if there's a value in there, then we're going to need to set that P quad phase output to 0.0, and we need to return 0.0 because there isn't a note on, and we need silence to be output. Right. What do we need to do next? Okay, so we need to set some values up. So let's create a double called D out. Set that to 0 initially, and we need a quad output as well. So double Q out. That's going to equal 0 as well to start off with. Okay. Right. So as I said, we've got this this concept. Hi Cody Beard, welcome. Good evening. Good to see you. Okay, so as I kind of indicated before, we've got this concept of this modulo counter, which is going to count up from 0 to 1 in various increments, and the increments going to depend upon the ratio of the frequency of the low frequency oscillator divided by the sample rate. So we need to know if we're going to wrap our modulo. So let's set a Boolean value up. and initialize it. This is going to be wrap. Are we going to wrap our modulo counter? And we can call, there's a function over here in our oscillator header file, which is check for wrap, and that does the checking is the modulo counter greater than 1 or less than 0, in fact, and it will take care of wrapping our modulo counter. So let's call that. What was it called again? It was called. Let's just grab hold of it. Actually, it was called check wrap modulo. So we'll do that first. Then we need to do different things if we're a one shot. So a one shot LFO is going to, when the player plays the note, it's going to start. It's going to go through one cycle and stop. A free running one is going to carry on, and a synchronized one is going to be synchronized to start again whenever a new note is played. So we need to take care of those variations. So what we can say is if the mode, which was m_u LFO mode, if that is shot and we've wrapped, then we want to if we've wrapped, it means we've gone through one cycle. We've gone from 0 to 1, which is one cycle of our waveform. That means we need to at that point stop. So what we can do, we can switch the note off. Let's grab that. We can say, as far as the LFO is concerned, the note is no longer running, and we can return 0, which is basically this code here. So let's just grab that, pop that down there. Okay, so that's the one shot. So let's just comment that. One shot LFO mode. If we're not in one shot, then we must be in synchronized mode or free running mode, which means that we're going to carry on producing samples from our waveform. In free running mode, we're just going to continue. We'll sample it whenever we need to. And in synchronized, we're synchronizing to the start or stopping of a note being played on the MIDI keyboard. So, okay, so what we need to now to look at the Q out. So let's change this to DQ out to be consistent with our Hungarian notation which we're following. So, so what should we have? Let's have a double. That we'll call it the quad modulo. So the quad phase, as I say, this is going to be the inverse. It's going to be a quarter of a phase out of step with the rest of the 90 degrees out of step with the rest with the oscillator. So if the waveform is starting at 0, the quad phase output is going to start at 90 degrees or pi over 2. If you like, if you want to work in radians. So it's a quarter of a cycle ahead. So we need, that shouldn't be 10, that should be 0. There we go. Okay, it's good job I spotted that. That of course caused very strange things to happen. Okay, so this is going to equal our modulo counter, which is a member variable. D modulo. D modulo. There it is. D modulo, and we're going to add a quarter of a phase to it. So simply adding 0.25 to it should advance the quad modulo if it's used. So let's do that, and then we need to know if we're going to wrap. So if the quad modulo is going to be greater than or equal to 1.0, then what we need to do is set the quad, so D quad modulo minus equals 1.0. So we're going to remove 1 from it. So remember, the idea of the modulo counter is that when it reaches, when it exceeds 1, it resets to 0 plus the amount by which it exceeded 1. So that's resetting the modulo counter for the quad phase output. Okay, so we've done that. Now we need to know what kind of waveform we're going to produce. So this caused me quite a lot of issues with switch statements last time, so try and be careful how we handle the switch statements. So what kind of waveform are we going to produce? So the internal value of this is going to be held in this enum here, and it is MU waveform up there. Let's copy that across. So we're going to switch on that. So let's try and keep close tabs on this switch statement. So if it's a sine wave, so I don't like the formatting of this, the way it's indented itself there. We see if we can override that. That's better, isn't it? Okay, so if it's a sine wave, okay, so I'm going to refer to my notes here for the sine wave because there's an algorithm behind this. This is the parabolic approximation to a sine wave, and we need to feed some values in based upon our modulo counter. This is basically the phase angle we're going to use. I'm going to use the formula I've got written down in my notes here. So the formula, it's a double, and it's called the phase angle, and that's going to equal our modulo counter, D modulo times 2.0 times pi, and then we're going to take pi off it. And then we're going to set D out to the output of our parabolic sine approximator. And the parabolic sine approximation is defined within the oscillator base class, I believe, or it could be defined within, I think it's defined within synth functions. So let's have a look at synth functions. And can we find the, I think it's called parabolic sine, there we are. And there's a helpful link there to where the formula comes from. This is the algorithm we're going to use to create a parabolic sine. So basically what this is we use a parabola to approximate the upward curve of the sine wave, and another parabola for the downward kind of lobe of the sine wave, and we join them together. And this basically saves us calling the sine function. And the sine function can be very expensive computationally, especially when we're producing pitched oscillators and there may be many harmonics. So we might, for example, if you wanted to work out the output of a pitched oscillator for the lowest A note on a keyboard, then there are 800 harmonics as far as the Nyquist frequency, which is the sampling rate, half the sampling rate in fact. That's about 22 kilohertz, which is the kind of upper limit of human hearing. So there's 800 different harmonics in that waveform, which means you'd call sine 800 times in that case, which would be pretty bad really. So this parabolic approximation is a lot quicker computationally, and it's not so heavy on the processor. So we want parabolic sine, and in here we pass in our angle, our phase angle, to come up, and it'll come back with a point on that approximated sine wave that we can pass out in our d out variable. And then we want to calculate the quad phase parabolic angle as well. So this is going to be basically the same thing. Let's copy this down. So the Q angle, the angle here, we can actually reuse the same. We'll reuse the same variable. And this is going to be our quad phase modulo, d quad modulo. Exactly the same calculation, and this is doing the dq out. And then we can break. We've calculated the sample which is going to produce from the LFO for a sine wave, an approximated sine wave. Okay, so let's see if we can keep this switch statement looking cool. So now we're going to do a unipolar saw wave or a bipolar saw wave. So saw wave, also known as a ramp wave or a sawtooth wave. So in this case it is a wave which, in terms of unipolar, it rises from 0 to 1. When it reaches 1, it immediately resets to 0 again. For the bipolar, it starts off at -1, rises at a regular rate up until it reaches +1, and then immediately drops down to -1. So I haven't got my. If there's any questions about what a sawtooth wave is, then I can draw it, but I haven't got OneNote running at the moment, so save that. Okay, so by definition, a one-shot saw wave from our LFO is going to be unipolar. So we can actually set that. We can say if U LFO mode is equal to shot, not equal to shot. Then okay, then we can convert a unipolar counter to bipolar. We say D out. We can take for the saw wave. A saw wave is basically it's the output of a modulo counter. So we can extract the samples for a saw wave directly from our modulo counter without any kind of fancy algorithms. What we're going to do here is convert it to a bipolar output there. So we're going to say unipolar to bipolar, which is a built-in function, and then we're going to say it's D modulo, wasn't it? Just pass in the modulo counter, and that will give us the sample that we need for our for our saw wave. And also the quad wave, we just do the same thing. We pass in the quad modulo. So the Q out is going to be, and this is going to be this D quad modulo rather than the regular one. So that else, then we say that D out is going to equal our modulo, D modulo, -1 because it's unipolar, and so is the DQ out. This is going to be quad modulo, D quad -1. So this is so I try to confuse you really by the definition of U saw and D saw. U saw is a sawtooth that goes upwards. So it let me get my tablet here. So to explain this, let's bring up Paint. So an up saw is going like this, and the down saw is basically going like this. If I can get it to draw, but you get the idea. It's up and down. So if we've got if it's a down saw, we just need to invert it. So we can say if underscore U LFO it's U waveform, that was it, is equal to D saw, and then simply we are going to just multiply by -1. And we're going to do the same for the quad. So DQ out multiply equals -1.0. Okay. And we can break then. So that's our up saw and down saw handled. So the next thing we need to do is a square wave. And in terms of the square wave, we can also extract this from our Modulo Counter quite easily. So this is a trivial square wave. So this is a mathematical square wave, which means it basically jumps instantaneously between -1 and +1, and then from +1 to -1. So that is really kind of bad thing in terms of if you were to listen to that, you get lots and lots of what we call aliasing. So lots of frequencies would appear in the spectrum of that signal, which shouldn't be there because the discontinuity, the immediate jump between plus and -1 causes severe kind of severe aliasing problems. And that's absolutely fine with an LFO. It's not an audible signal. We're using it to control things. When we come to writing our pitched oscillator, which we probably won't get through today, when we come to doing that, then we need to be much cleverer about our square waves and indeed our sawtooth waves. We can't have those vertical, the instantaneous switch between plus and -1 in those signals, which is why we're going to be using analog modeling pitched oscillators. So we're going to use a technology called BLEP, B-L-E-P, which is stands for bandwidth limited step, and it basically is a way of smoothing out those rough edges of those square waves and triangle waves and sawtooth waves, so that the spectra is purer. It doesn't have all the aliasing, or at least it reduces the aliasing. We're also going to come in to a point where we can use lookup tables, wave tables, and those wave-table derived waveforms don't have any aliasing by definition because we've calculated them out of it basically. But in this case, it's going to be what we call a trivial square wave, as these were trivial saw waves. We're simply basing them straight off of our Modulo Counter. So in this case, D out is going to equal our modulo, D modulo, and we're going to have a ternary expression here, so that if that is greater than So we're going to introduce the concept of pulse width now as well. So if I can get this working, let's not have paint, let's have one note. Let's explain pulse width. Let's clear this away. This is our design for nanosynth. Come on. There we go. It's like cleaning the blackboard without all the squeaky and this squeaky kind of chalk rubber and the nasty chalk dust. Okay, so in terms of pulse width, let's convert over to a pen that we can see. When you have a square wave, you could have it so that the positive side was narrow and the negative part of it was wide, like that. Or you could have it the other way around. You could have it so that it was positive for a long time and negative for a short time. Or of course you could have it equal. But this width here is the pulse width. So we want to be able to control that. Our current oscillator doesn't have control over that, but we need to build that kind of capability in. So let's do that now. So we've got a pulse width variable in our base class, I believe. Pulse width control, pulse width, pulse width. There's pulse width. This is it here. M pulse width. Let's grab hold of that, and we'll say that if that divided by 100. So this is a percentage now. So what we took when we have pulse width, we talk about it being 50% pulse width, which is equal positive and negative values. 80% pulse width would mean that 80% of the time the signal was +1 and 20% of the time it was -1. So we need to look at this value, and we'll output either a -1 or a +1 depending upon the value of modulo, whether it's greater than the pulse width percentage or not. So if it's greater than that, we need to output -1.0, else we'll output 1.0. So that is obviously the definition of a square wave. It's either +1 or -1. And we can do the same with our quad outputs. So we'll replace that with that, and then we can break, and that's our square wave, our trivial square wave. So this is, it really is, it's going to jump instantaneously between plus and -1. Which to say isn't a great thing to listen to. Well, isn't the best thing to listen to. I mean, we did that in our .NET Core synthesizer, and it wasn't too bad, but when we looked at the spectrum analyzer that FuelStable PR'd into the project, there was an awful lot of frequencies in there which shouldn't have been. So we're going to take care of that with our pitched oscillators. We're going to by using the analog modeling oscillators rather than the simple mathematical formulae here. Okay, so we've got triangle wave now. So let's try. Okay. So we can calculate a triangle wave from a saw wave. So let's grab this, our saw wave output. Okay, so I'm going to have to refer to my notes on this because this is obviously a mathematical operation we're going to have to do. So we're going to take the absolute value of this output, multiply it by 2 and take 1 off it, and that should generate a triangle wave for us. So we can say that D out we're going to change it to be 2.0 multiplied by, so we want the floating point absolute value and of D out, and we'll take 1 off that. And that is the algorithm to create a triangle wave based upon a sawtooth wave. Now, that is a bipolar triangle, so it's going between plus and minus 1. So it's a triangular wave going between plus and minus 1. Okay. Now, if we're in one-shot mode, then we need to change that back to being unipolar, because one shot by definition is goes between 0 and 1, not between minus 1 and plus 1. So if the mode, LFO mode, was shot, then D out is going to equal, so we have a function that's the same, we got, instead of unipolar to bipolar, we've got bipolar to unipolar, and we'll basically pass in the value of D out into that. Okay. And we can do exactly the same thing for our quad phase. So let's put that in there. So DQ out is going to equal that. This is going to be our D quad modulo, and we can say exactly the same. DQ out is going to equal that. Q out, and the same here. If we're in one-shot mode, we're going to simply change it to unipolar. And we should be able to break at that point, and that's our triangle wave sorted. I think I might have missed. Well, we'll deal with the RSH and the QRSH now. So I think I might have missed a type of LFO waveform. let's just sort this out first. So RSH, which was the random shot and hold, and then there's the quad phase version of that. So when we got this random shot and hold kind of idea, it's slightly more complicated than we've had so far. So we need to know whether this is the first time we've run through the random shot and hold. So we've got this. We've got a counter somewhere which counts how many times we've done this random shot and hold. Where is it? There it is. The random sample and hold counter. So we need to know something about that. So if that is 0, or if it's less than 0, we know that we haven't actually been through this process. So if that is less than 0, then, so if our LFO waveform is going to be RSH, which is random sample and hold, not shot and hold as I've been saying, then we want to say that our RSH value is going to be basically we generate some white noise, and we take a sample from that white noise, and that is the first random sample. So we have a function which is do white noise, and into there we don't have to pass anything. We just get a random white noise sample at that point. If it's not RSH, then what we need to do is take the value, and I need to refer to my notes again here. Okay. So this is, we need to do this is pink noise. Should do pink noise sequence, and we're going to pass into there. We're going to pass in a register. So this is M. What's it called? PN register. So this is something we haven't talked about. So, but we'll skip over it for now. And then we're going to say that we're going to set the counter to 1. RSH counter equals 1.0. So basically we're getting a kind of a starting point for our random sample and hold values. Okay, so basically what's going to happen is this counter is going to count down, and we're going to say, okay, when the counter has expired, then we're going to get a new random sample and hold that for the time. So we can say else. And in this case, it's going to be else if so M RSH counter is greater than the sample rates. So we've got M it's a double. This Hungarian notation confuses me. I'm sorry, it's just not something I'm used to. And we need to divide that by the frequency of our low frequency oscillator. So that's going to be a double again. An F0, that is basically the frequency of our oscillator. So if we've exceeded that, then what we can do then, we know that our hold time is exceeded, so we need to generate a new. We need to kind of decrement our counter. So M and RSH counter minus equals, and we just take the frequency here. Decrement it by that. That's the inverse of our modulo counter increment, actually. And we can say that if our waveform is RSH, then our value, our new value that we're going to output is going to be do white noise again, another random sample, else it's going to be that. Then we need to increment our counter, so M and RSH counter plus equals 1.0. output the values. So D out is going to equal the what's it called? The RSH value. And break. And we have a default. We simply break on default. We think to do in that case. Now there's one I missed, which was let's just indent this. So there's an exponential as well, which is a case I missed. I think I missed that from the controller, so I must make a note to do that. Okay. Let's check my notes down here actually. Yes, I've missed it off. So let's go and put that in. Let's save here and let's go and fix that up. So the LFO waveform, let's right click on that. So we've mixed expo from this exponential. Okay, so that's added that. So exponential. Okay, so the exponential ones, we've got mathematical functions built in for us to calculate these. So I'm just going to call those directly without explanation. So for the D out, we have something called concave invert transform, and we pass in the modulo value. And for the Q out, we do the same thing. We're passing in here the quad modulo. Let's go and have a look at what concave inverted transform does. So it says it calculates. Okay. So basically, it is an exponential function which is using this as the value. So we get a value in, which is the value of our modulo counter, and it's saying the return value is minus 5/12 times the log base 10 of the value passed in. Okay, so this is why I don't really want to go too much into the mathematics, but that is the function that we're using to calculate this exponential value. Once again, as you can see, it's going to be kind of limited by this convex limit, and we've got concave and concave inverted, which is interesting because this takes 1 minus the value. So I haven't quite got as far as this in my DSP book that I'm reading. I've got a really interesting book called the Digital Signal Processing Primer, which covers all of these algorithms. But so this one here, we'll just have to accept for now, and I'll explain later when I understand exactly what it's trying to do. Okay. So that has taken care. So what we've done there, we've got a big switch statement, which is basically setting up our output values for D out and DQ out. And now when we reach the end of that switch statement, we need to increment our modulo. And there is a function we do that called inc modulo. And what that's going to do, it's going to increment our modulo counter by a value which is the frequency of our low frequency oscillator divided by the sample rate. Sample rate is going to be 44.1 kilohertz, and the frequency of our low frequency oscillator we set that was going to vary between basically 0. There was a small negative in there, basically 0 to 20 hertz. so below the range of human hearing. We also need to deal with our quad phase, so we can say that if that point has a value, that quad phase output has a value, then that pointer, the quad phase output, is going to equal the Q out multiplied by the amplitude of our, need to be a lowercase, so we need to multiply that basic value between 0 and 1 by the amplitude that we set for our low frequency oscillator, which is m d amplitude, and also multiply that by any kind of modulation, mod. And then we can take that calculation there and we can simply return the out multiplied by those values. We don't need the equal sign. So let's see if that builds. We'll build it from within RackAFX rebuild. So we got a redefinition of a default argument, parameter 1. Redefinition of default argument, parameter 1. What does that mean? Redefinition of a default value. I think this should be is that how it should be? No, I think it's definitely right like that. Do we just not have that? Is that the trick? Let's try building that. Rebuild. Unresolved external symbol public virtual. Unresolved external public virtual. I should tend to think that that should be that, wouldn't you? Not sure if you saw this shader last time. Fjords Neighbour says audio shaders as well as graphic shaders. You like that one particularly? We'll have a look at that in a second. I'm trying to figure out what this is trying to tell me. Build it. Redefinition of default argument. It says public virtual. Is it because I haven't defined a destructor? Try that. Yeah, it's happy now. Okay, so it was because I forgot to create the destructor. Yeah, I forgot to implement method. That's exactly what it is. So if you're stable, let's go and have a look at your audio shader toy. That's fantastic. It's someone else's. So this is basically responding to the music. Or is it generating the music? You've got ring modulation on there looking. Excellent stuff. Well, there's a whole world out there which you don't really know exists, isn't there? Yeah, fantastic. Okay, so how long have we been going now? So we've been going an hour and 25 minutes, so we should be able to get a bit more done. So that's our low frequency oscillator class created. Let's make a start on our pitched oscillator. This is going to be what we're going to call a quasi band limited oscillator. So we're going to use this concept of bandwidth limitation in order to model an analog oscillator. This is a bit more complicated. Once again, I'm not going to go too much into describing exactly how this works, but the main point is it's going to produce. We're going to have two of these, and they're going to be linked and mixed together, slightly detuned from each other, and it's going to produce hopefully some really nice sounds which have a purer spectrum than if we just implemented mathematical formulae like we did in the .NET Core 3 project that we did for a synthesizer. And all these objects we're creating, the LFO and the quasi band limited pitched oscillators, are all reusable objects, so we're going to be able to use them later. So I'm not too sure how far we're going to get with this, but let's make a start. Okay. What's the best place to start with? Okay, let's create a header file. We're going to call it Crazy band limited oscillator. Band limited. That's supposed to be a limited, not limited. Okay. So let's go over to here. We're going to want something pretty similar to this. Let's just grab this for a start. So our crazy band limited. This is going to be called C, crazy band limited oscillator. Once again, it's going to inherit from our oscillator class. We need a constructor and a destructor. We need we've got reset, that. We're going to need some more functions. So we're going to, this is going to output sine waves or sawtooth waves, triangle waves, etc. So what have we got on our oscillator here that we can override? So I think the basics, we've got to implement the pure virtual methods, but we need some other methods in there, basically. So let's have a look at what we can do with what we've got here. Let's create a Cpp file. This once again is going to be called crazy band limited oscillator. We'll put the pragma in, and we'll also include crazy band limited oscillator.h. Okay. Right, so over here we basically built a constructor and a destructor. Let's just pinch that code. This is going to be limited oscillator. We don't need any code within there. Over here we are building the, so did we put the C in front of it? CQB limited oscillator. Make sure we copy the same name across. Oh, I see. I put an I on there. That's the problem. Fat fingered SMB as usual. There we go. That should be happy with that. Okay, we need a reset. So void column reset. Remember, reset basically restarts our oscillator. So we can call the base class C oscillator reset here. However, we need, if we got a triangle or a sawtooth wave, we need to start in the middle. We need to start at 0, which is not where those waveforms start. They start at -1 or whatever, or whatever. So we need to start them kind of halfway through their cycle. So we can say here that if our U waveform is SAW 1, and we got 3 types of sawtooth wave we're going to produce. So that was try, I think it wasn't it, try. Check those values. 3, 2. Then we're just simply going to start those halfway through. So basically, with our modulo counter, we're going to start it at 0.5 rather than 0. So you understand that's actually because we want to start with the value of 0, and our modular counter is going to be counting when we turn it into a bipolar sawtooth wave or triangle wave. It's going to be counting up from -1. So that's basically all we need to do there. With the start oscillator and stop oscillator, we can just go and take the code directly out of here. So start and stop oscillator, we can take that code and pop it over here. The code's going to be very similar. There isn't any concept of the shot though. So when we start the oscillator, we want to reset to the starting position for the wave, and then say that we have a note on incident, a note on case. So we are playing a note, and when we stop the oscillator, we say we're no longer playing a note. Okay. So we're going to do. Let's see, what's the time now? We should be able to do some of these. So let's do the do sawtooth. So we'll inline this. We're going to produce a double out of it, and we're going to call it do sawtooth. We're going to pass into there our modulo counter and our increment. So both those are doubles. So we've got a demodulo and an increment which is also double. So remember, the modulo counter and the increment, they're coming from the trivial generation of a sawtooth. So what we're going to do to create an analog modelled sawtooth, we're going to create a bipolar trivial sawtooth wave, which is basically taking it directly from the modulo counter but making it bipolar. By bipolar I mean it's going from -1 to +1 rather than 0 to 1, which is unipolar. We're going to apply a bit of wave shaping, and we've done this before. We're going to smooth some of the edges, the rough edges, over by applying the hyperbolic tangent function. And if you watched the streams I did on the .NET Core 3 synthesizer, you saw me use hyperbolic tangent to smooth out rough edges on waveforms. So basically what it does, between certain values, the hyperbolic tan function is a linear function, but as it approaches -1 or +1, it kind of tails off towards an asymptote. It never reaches -1 or +1, but it kind of forever it reaches those values at infinity. So it gets closer and closer and closer to the value of -1 or +1, but never actually reaches it. It gets closer and closer, and you could say it reaches those values at infinity. This means that you no longer get this kind of sudden transition to plus or -1. It constantly approaches those values, and that's called wave shaping. And we're going to apply that to our sawtooth wave, and then we're going to use this concept of a bandwidth limited steps, which I'll describe, I think, in another stream. I think I touched on it in the last stream. In fact, I'll just kind of describe what we're going to do, and it's about this. The idea is, and it's not going to be that easy to actually show you because my drawing on here is going to be pretty awful, but with the sawtooth wave, it ramps up and then it drops immediately down to the minimum value and then ramps up again. Okay, and these are supposed to be, in fact these lines don't really exist. It just ramps up from -1 to +1, and then immediately, as soon as it hits +1, it drops down to -1 again. So that line, strictly speaking, isn't there. But the existence of that discontinuity, when it falls off a cliff and immediately changes value and sign, causes all the aliasing issues we have with using these mathematical functions to create audible sounds. Because we're now working on something we're going to hear, a pitched oscillator. So what we're going to do, we're doing some wave shaping to smooth these out, but we still have this discontinuity. So our wave shaping is going to smooth this bit out a bit, like that. But this discontinuity needs to go away, and what we're going to do is we're going to kind of replace this discontinuity with a curve. It's exaggerated, so it's all going to be rounded, and it's never going to be a vertical drop. It will be quite steep, but it's never going to be a vertical drop. And the inserting of this segment of the curve in there is what this blep process is meant to do. And what we're going to do, it's quite simple. It's not as complicated as it sounds. There's a mathematical formula which we're going to exploit. It's already built into our synth functions. We don't need to know about how it works. But basically, we're going to put in an extra sample. So instead of it going when it kind of gets really close to +1 because we wave shaped it, and when it would have dropped, we're going to put a sample either side. It's hard to say. Let's get rid of that. So what we're going to do, we're going to go up, and we're going to insert a sample either side of this discontinuity. So it will in fact appear to be rounded at the top and have some kind of, and it'll be rounded at the bottom as well. It will have a slope to it. So this is much more like an analog electronic circuit involving resistors and capacitors and things generates when it generates a sawtooth. It never generates a perfectly mathematical one. And of course, because it's analog, it has that sound of analog synthesizers, and it sounds good. It doesn't have the aliasing which is introduced by the fact we're using a digital source. So it kind of gets around all of that. There are the three ways we can generate those, insert those curves to kind of smooth it out, those samples. There's one which is 2-point blep, 8-point blep, and poly blep, and we're going to use 2-point blep. So all we're going to do is create two extra samples either side of that where that discontinuity should have been, and that will just creating two samples will eliminate 90-95% of the aliasing and make it sound great. We can use the poly blep, which is using a polynomial function to calculate what that curve is and get the samples, or we can use more points either side, so it's more accurate. But it doesn't actually matter because 2 points will be good enough. And we can come back at some point and experiment with using 8-point bleps and poly blep. 8-point blep has limitations though. We can't use it for high frequencies, basically because we run out of samples. We can't actually find 8 samples to insert. Okay, so let's start doing the sawtooth wave and see how far we get. So we're going to create a trivial sawtooth wave first. So D trivial sawtooth. We start that going to start at 0, and then we're going to say we've got a double, and we've got this D out again, just like we did before. We'll initialize that to 0. Okay, and then we're going to say, okay, if the waveform waveform why isn't it finding that? MU waveform. Did find that? Okay, well, why isn't it finding that value? We're bringing oscillator in, aren't we? UV limited oscillator. That brings in oscillator. Okay. Not sure why that is required. Okay. What's going on there? We managed to get this working over here. Okay, this is a bit weird. So I've obviously made a mistake somewhere. That's because this needs to be presumably that. And do I need to? I need to prototype them in my over here. So this will be double do Sawtooth, double do Modulo, double D. So that's happy now. Okay. Still not quite used to the concept of defining things twice, but there we are. Okay. So if that's saw 1, so this is saw 1 is a normal ramp. So trivial Sawtooth is going to equal unipolar to bipolar. I'll pass the modulo in, D modulo. Okay. I'll see if that's going to be saw 2, which is a one-sided. We're going to use a one-sided wave shaper on this, so we're going to shape one side of the wave with the tan function, tan H function. So D trivial Sawtooth again. And that's going to equal 2.0. So I'm just looking at my notes for this. 2.0 multiplied by. So this is going to be. So we need hyperbolic tan H. And we're going to take into tan H. We're going to take. Okay, so I won't go into why this is like it is. 1.5 times the modulo. So a lot of all these kind of these algorithms can be found on the internet if you're really interested, and we will go through some of them. And this is going to be 10H of 1.5. And On top of that, we are going to take 1 off that. So let's see. So then, else if the waveform, is saw 3, which will be in a wave shape both sides of the Sawtooth wave. So this is just shaping one half of it. So we're going to do the make it bipolar, and then we're going to apply a similar function. So let's be careful what we do here. So this is going to be that. It's going to be. It's not going to be 2 times anything. It's going to be just that, I think. So this is one-sided wave shaping. This is dual-sided. The hyperbolic tangent function. Okay. And now we're going to do the blep correction. Okay, so this is where we're going to get rid of that discontinuity and make it appear as if it's got a curve in there. And it's really amazing that you can just insert two samples, and when your digital to analog converter sees that, it will actually kind of fill in the rest of the wave, which is part of the magic of digital sound, really. So D out now is going to equal our trivial saw, and we're going to add into that a value which is going to be calculated by our blep. Now this, once again, I'm going to have to look at my notes to get this. It's a completely non-trivial piece of code. You couldn't work it out really unless you work through your algorithms. So let's pop the code in. So there's a function called doBlep. We need to pass some values into that. So the first value we need to pass into it is a pointer to a lookup table. So we're going to give it an address. It's the blep table. I think it's 4096. Which is the size of the blep table array, and then we pass in the modulo that we've got, so it can go and find out what the value, the correction value is for our modulus, and then we pass in our the absolute value of the increment, and then we pass in 1.0, and then we pass in false, we pass in 1, and we pass in false. So let's go and that needs to be the absolute value of the increment. Do blep, it says it's undefined. I think it's do blep. Do blep n for the nth sample. Okay. So what's it we're expecting? It's expecting. So it's got the blep table, the table length, the modular value, the increment value, the height. Is it a rising edge? The points per side, which is the 1 point either side, so it's not a rising edge. And do we want to do linear interpolation, which is we set to false. So it's complaining, isn't it, about my ampersand there. That's the blep table. You can see the blep table in the preview here. These are all the corrective values. For small values, they're tiny. What's he complaining about that for? Somebody wants to return D out at this point. Let's build that and see if it tells us why it doesn't like that ampersand there. Arguably type const double is incompatible with parameter type const double. Expected declaration. Okay. Let's see if we can build. Okay, I haven't defined do oscillate, so it's not building. Okay, but that is interesting. I thought there should be an address dereference in there. Okay, well, we'll see. What's the time? We've been going for nearly an hour now. Let's see if we can do the square wave. So we're going to do square. Like that. We're going to want to have a similar definition. Do square. Okay. And we're going to return out at the end of that function. Okay, so we need to build a square wave, and we need to build a square wave which doesn't suffer from all the aliasing problems if we use a mathematically perfect square wave, which is simply a value which swings between plus and minus 1 and stays at those values for a certain time, called the pulse width. So we need to generate this in such a way that it's going to emulate, it's going to model an analog circuit. So that wouldn't produce perfect discontinuities, and if it did, it would sound awful. So that's what we're going to try and do. We're going to use a technique called the sum of sawtooth waves. square wave using sum of Sawtooth method. Once again, this is an algorithm you can investigate online, or you can buy a book and read about it. But it starts off, we need a basic Sawtooth wave, a Sawtooth wave, which, you know, but the basic one, which is a normal ramp Sawtooth, i.e. that. So let's grab that bit of code and stick that in here. So we're going to set our waveform to be a Sawtooth, and then we're going to do Sawtooth to get a value. So we're going to say double, and it's going to be the saw is going to equal do Sawtooth, and we're going to pass in d modulo and d inc. That's going to give us, that's modulo. So that's going to give us a Sawtooth wave, or a sample from a Sawtooth wave, basically. So if our increment is greater than 0, we have a positive frequency. So this is to do with having dual oscillators. What we want to do here is to modify the oscillator. So the first oscillator is going to produce, it's going to have the pulse width on the positive side, and the second second oscillator is going to have your pulse width calculated on your negative side. So we can say d modulo is going to equal, going to add the pulse width as a percentage. So m pulse width divided by that, else it's going to be, we're going to take that value off. But remember, we talked about square waves, we've got this idea of a pulse width. Okay, so this is for positive frequencies. And this is for negative frequencies. Okay, so for positive frequencies, we need to generate, we need to change the modulo. So what we're saying here is that if the inc is greater than 0, the frequency is positive, and the modulo, d modulo, is greater than or equal to 1, then we need to take 1 off, and we need to do the we need to flip it. So the modulo, you take 1 off the modulo, basically. The d modulo minus equals 1.0. And similarly, if it's a negative frequency, that is less than 0, and that is less than or equal to 0, then we need to add 1 to it. Okay, so we now need another Sawtooth wave. So let's call this saw 1. Let's generate Sawtooth number 2. Remember, we're doing sum of saws. Saw 2. Passing the same values in and get another Sawtooth wave. And we're going to add those together. So we can say that d out is going to be equal to. So we're going to take half of. We need to define d out. d out is going to be half. We're going to equal mix of the two sawtooth waves. So we're going to mix them together. So we have d saw 1, and we're going to add, and we're going to subtract 0.5. D saw 2. Okay, when we do that, when we add two sawtooth waves together, if they've got any kind of pulse width which isn't 50%, when you do the addition or the subtraction, there should be a multiplication there. When you do that, unless it's 50% pulse width, you're going to get a small positive or negative value as the result, because the area under the positive side of the square wave will not be the same as the area under the negative part of the square wave. And if you kind of integrate that, you look at what the residual of that is. If it was a 50% pulse width, then the positive side would exactly equal, and the average value, the average sample, would be 0. But in the case when you have a pulse width which isn't 50%, you can have a positive or negative, what's called a DC offset, a direct current offset. So as if there's actually a current flowing, there's a constant signal in the background which will be audible, and it will actually kind of ruin the sound. So we need to get rid of that, and it's a corrective factor. So we need to create a corrective factor. So our corrective factor D that's going to equal 1.0 divided by the pulse width as a percentage, which is this here. Okay. So basically what we need to do is work out whether the percentage pulse width is less than 0.5 or greater than 0.5. So if that value is less than 0.5, then the corrective factor is going to be slightly different. Its corrective factor is going to be almost the same, but it's 1 minus that, 1 minus percentage, the pulse width as a percentage. Okay, and then we need to just basically multiply our sample by the corrective factor. So D out times equals D corrective. Then we can set our waveform to be the correct value. So M U waveform is going to be equal to square. And we can return our value. Okay, so that's the square wave. We also want to do triangle waves. How are we doing for time? Okay, I'm just going to be right back just for a second. And apologies for that, I need to just put the ovens on because I'm getting hungry. The oven's got to warm up. Okay, so do triangle. I don't think we're going to have time to do the triangle waves, but let's set up the basics of it. So this is a bit more complicated. It might be worth trying to explain how a triangle wave can be generated. And we'll say double d out equals 0.0, d out. Okay, let's see if we can create it. So this is so there's an algorithm I've got written down here in front of me. So this is slightly more complicated. It's to do with we create a sawtooth wave. So a lot of the times these algorithms are based off the output of a sawtooth wave. We're going to square the sawtooth wave. This kind of gives a parabola. Obviously, square. You know, remember if you do the kind of the output of a function which is squared, y equals x squared. That plot that graph, you get a parabola. So we're going to square the output of the sawtooth wave. So we're getting a parabolic output at that point. We're going to multiply by -1, and then we're going to modulate that output and do differentiation. And there's a corrective factor as well, which we've got to apply, which is similar to the kind of corrective factor we have here. So I think the best thing we can do is to actually just code it up. So there's more values we need to put in than this. So let's go and change our prototype. So we're going to have our modulo. Let's just fix up these names, which are really weird. Okay, so we need the frequency, which is by convention we're using FO, but it's F0 really, the frequency of the wave we want. Something called, so that's a double. We want some kind of modulation factor, which is going to be a double. And this, we're going to call this the square modulator. And we're going to take in a pointer to a double, which is going to be something called the PZ register. So this is to do with the differentiation we're going to have to do. So we'll just copy these values across, and I'm going to stop at that point. Let's just add those in there, because this is a bit more complicated and probably would benefit from better explanation. Okay, so let's commit this to Git. Episode 57 started oscillators, and we'll finish this off next time. So the next stream will be tomorrow at 8 o'clock. I'll sync this up to GitHub, and we'll be doing part 2 of our look at T4 templates, and Morton is going to be joining us again for that. That's Pure Stable from chat. So that's tomorrow at 9 o'clock, 8 o'clock, sorry, UK time. There won't be a stream on Wednesday because I'm fortunately having to work late, so I won't be available at the normal 4 o'clock slot. So I'll try and squeeze in another slot. So watch Twitter for that, and also Discord. Let's now. So that's been. Let's just make sure that did that build or not, or just broken the build. It didn't build. Okay, let's see if we can fix this first. Oh, I haven't done do oscillate yet. That's the reason. In fact, if we just to fix that up, let's grab Do Oscillate from here. So what did Do Oscillate look like? Look like that. We'll just drop a Do Oscillate in here. And we'll just do the same kind of thing. Yeah, we're okay now, so let's just recommit that to GitHub. There we go. Okay, so let's find someone to raid, and you can spend the rest of your evening with another streamer. So let's have a look. Who have we got? Looks like the Michael Jolly is streaming us. Oh, Javid as well. Let's see if we can go to Javid X9. Oh, Brave Cobra. Let's go over to Brave Cobra. I've not seen him stream for quite a while. Let's raid stream Brave Cobra. So do stay with us for that. Thank you for joining me on this pop-up stream. And I'll see you tomorrow for more T4 templates. Take care, everybody. I'll see you then.